Welcome back to the deep dive. If you're here, it's because you want, well, a shortcut to being truly well-informed. And today, we are taking on probably the biggest source material imaginable.
It's definitely up there.
Yeah, we're embarking on a pretty high-stakes investigation here and looking into the foundational questions of modern science. We're talking structure, evolution, the ultimate deep-time fate of the entire observable universe.
Yeah.
And we're drawing from a really classic piece of cosmological thought that lays out the evidence for the Big Bang and,
Yeah.
well, everything that follows.
It really is an immersion into pure physical reality, and the scope is just immense. This material tackles what scientists call the cosmological problem,
Okay.
which is really the intellectual quest to understand the observed structure, the development of the entire cosmos. How big is it? What's its geometry? And fundamentally, what's causing that observed redshift, this apparent running away of galaxies from each other?
That sets the stage perfectly, I think. We're literally going from the very earliest fractions of a second we can even conceive of, all the way to, well, the heat death of matter itself, trillions and trillions of years down the line.
An unbelievable timescale.
Right. So our mission today is to distill the key arguments, the surprising insights, and maybe most critically, the observational breakthroughs that really cemented the evolutionary view of the cosmos. This idea that the universe changes, like, radically over time, and what that implies for life, for us.
Exactly. What these incredibly precise cosmic rules mean for the existence of complex life.
Okay, let's dive right in. Let's start at the beginning, or maybe the earliest point our current physics lets us kind of wind back to. It all starts with that simple observation, right? Expansion.
Precisely. The foundation of modern cosmology is that observed flight of the galaxies. Our best understanding suggests they're flying apart, and the speed increases by about 50 kilometers per second for every million parsecs of separation.
So the further away something is, the faster it's moving away from us.
Exactly. It's a clear relationship.
So if we take that observation, that everything's moving apart,
Mm.
and we, like, run the film backwards in our minds,
Yeah.
what happens? What's the extrapolation to the beginning?
Well, when you extrapolate that observed movement backward in time, you arrive at this, well, astounding, really necessary conclusion. Roughly 20 billion years ago, the entire observable universe, everything we see, was concentrated into an extremely tiny region.
Wow. Like all the stars, all the galaxies, all that empty space squeezed down.
Squeezed into a space far, far smaller than, say, our solar system. It's hard to even picture.
And that kind of compression, it must mean an initial state of matter that's just completely alien to us, right? Incredibly dense.
Oh, unbelievably dense. We're talking about density comparable to a single atomic nucleus. Figures like 1014 to 1015 grams per cubic centimeter.
Okay, hang on. 1014 grams per cubic centimeter. What does that even mean? Give me some perspective.
Right, it's abstract. Imagine taking the entire mass of Mount Everest and crushing it down to the size of a single grain of sand. That's the kind of density we're dealing with.
That's insane.
And it has to be, because at that point, matter wasn't atoms. It was this incredibly hot, dense plasma of fundamental particles all jammed together.
And can we push that even further back? What's the absolute limit?
If you push the extrapolation back even further to the very first tiny fractions of a second, the density actually exceeded nuclear density. The universe, in effect, was one single, unstable, gigantic supernuclear density particle.
A single particle containing everything.
Essentially, yes. And the cosmic expansion we observe today, it's really just the leftover consequence, the aftermath of that initial particle becoming unstable and exploding violently. It's an observation tracing back to a real event, not just some abstract theory we cooked up.
Okay, so this extrapolation, it naturally leads straight into maybe the biggest philosophical question ever, right? If everything was a single dense point 20 billion years ago, doesn't that just scream beginning of light or, the actual creation of the world?
And this is where science has to be really careful, draw a very firm line. And our sources tackle this directly, offering a crucial scientific caveat.
Okay, what's the caveat?
If this hypothesis, this super dense nuclear drop idea, is correct, then concepts like beginning or creation actually stop being useful scientific terms to describe that event.
Why? Because the physics breaks down.
Pretty much. The densities and energies are so extreme that our very concept of physical time as we experience it, time governed by the physics we currently understand, just loses its visual, its intuitive meaning.
So talking about what happened before that moment, it doesn't make sense because before itself might not have existed in the way we think of it.
Exactly. You can't apply our everyday macroscopic understanding of time to a singularity like that. We're in a realm where completely new physical rules must apply, probably involving quantum gravity laws we haven't fully worked out yet. Assuming our clocks worked the same way back then is, well, it's not a scientific assumption.
And obviously, life as we know it.
Utterly impossible. No space, no chemical complexity, no time for development, just pure high-energy physics.
It's crucial to remember, though, this Big Bang model, this evolutionary picture, it wasn't always the only idea out there. There were some pretty sophisticated alternative models that failed to account for evidence. What was the main challenger?
Yeah, for a long time, the primary challenge came from the idea of a pulsating universe. This model tried to keep the universe sort of eternally existing by suggesting it cycles endlessly between expansion and contraction. Maybe it had already done this countless times before our current cycle.
Like a cosmic breath, in and out.
Something like that. But the observable data pretty quickly put limits on that idea, at least in its simplest form. This brings us to a really elegant thermodynamic proof, what the source calls the almost helium problem.
Right, the helium problem. Explain that.
Okay, so stars, they constantly fuse hydrogen into helium. It's essentially a one-way process in stars, very irreversible. If the universe had been cycling like this for, say, hundreds of billions of years, but always staying below nuclear densities during the collapses.
Meaning it didn't get hot and dense enough to break the helium back down.
Exactly. If it stayed below that threshold, then over all those cycles, more and more hydrogen would have been converted to helium. The universe would be thermodynamically old. It should be, as the source puts it, almost entirely helium.
And if the universe was mostly helium, what would we see today?
Well, the stars would look very different. They'd be extremely dim because they would have burned through most of their primary hydrogen fuel ages ago. The fact that we see so many bright, active, hydrogen-rich stars today, that's clear proof the universe is thermodynamically young. It simply hasn't existed forever in this current star-forming state. The chemistry of the stars acts like a cosmic clock, ruling out that simple pulsating idea.
But there was a way around that, wasn't there? A more extreme version, the Phoenix model.
Yes, there was a mathematical loophole, if you like. Limitless pulsations are theoretically possible if, in every single cycle, the universe collapses all the way down to nuclear densities or even beyond.
So it gets crushed so hard it resets everything.
That's the idea. This extreme compression would, in theory, break all the helium nuclei back down into individual protons and neutrons. It would effectively reset the matter, erase the chemical history of the previous cycle, lose its identity, so to speak.
The universe essentially destroys itself completely and starts over, chemically speaking.
Precisely. Now, while that solves the almost helium problem on paper, our sources point out it's, well, philosophically not very appealing. It means there's no overall long-term development or evolution of the cosmos. If everything gets wiped clean every 100 billion years or so, there's no grand cosmic narrative, is there?
Yeah, history just keeps getting erased. Okay, what about the other big contender? The one that held sway for quite a while, the steady state or unchanging universe. Fred Hoyle was a big name there.
Right, the steady state model. This proposed that the universe, on the grand scale, looks the same at all times, even though we clearly see galaxies flying apart.
How do they square that circle? If things are moving apart, how does it stay the same?
It required a pretty radical idea. The continuous creation of matter. Essentially, new hydrogen atoms would have to be constantly popping into existence, literally out of nothing, in the expanding gaps between galaxies, just enough to keep the average density constant over time.
Which I guess back then might have seemed even weirder than a single Big Bang event.
To many, yes. It seemed like a bigger violation of known physics creating matter from nothing. But its proponents argued it preserved a kind of eternal symmetry for the universe.
Did that idea evolve at all?
It did get updated. You had people like A.D. Lin much later, in 1986, suggesting a variation where this continuous creation wasn't from literal nothing, but maybe from a kind of high-energy vacuum state. This vacuum could spawn expanding bubbles of ordinary matter, and our observable universe would just be one such bubble. But again, as we'll see, these elegant theoretical ideas eventually crashed against hard observational facts.
Right, because all these theoretical debates, fascinating as they were, ultimately had to face the music from observational astronomy. The universe just wouldn't cooperate with the static models. The first really big blow came from radio astronomy in the deep past.
Yes, this was absolutely crucial. Radio telescopes have this amazing ability to see incredibly far, piercing through dust and gas. This means they can effectively look back in time billions of years because the light, or radio waves in this case, takes so long to reach us.
So we're looking at the universe in its youth.
Exactly. By studying very distant radio galaxies and quasars, these are objects so far away that relativistic effects become really important. We're directly comparing the universe as it was back then to how it is now in our local cosmic neighborhood.
And what did that comparison show? Did the past look the same as the present?
Not at all. And this delivered the formal exclusion of the steady-state model. The observations clearly showed that the spatial density, how many there are per unit volume of space of these active radio galaxies and quasars, billions of light years away. Well, it's significantly higher than the density we see nearby, say, within a billion light years.
So wait, when we look far away, which means looking back in time, we see more of these superactive objects packed together.
Precisely. It means the ratio of these highly energetic radio galaxies and quasars to sort of normal, quieter galaxies was much higher in earlier cosmic epochs.
So the universe was different billions of years ago. More active, more energetic structures.
Definitely. Therefore, it evolves. It isn't unchanging. It hasn't been unchanging. That single observational fact really made the original steady-state model untenable. The universe clearly has a history.
But the real knockout punch, the discovery that just completely settled the debate, came almost by accident in 1965, didn't it?
Yeah.
Relic radiation, the cosmic microwave background, CMB.
Oh, absolutely. A genuine cosmological thunderbolt. You had these two engineers at Bell Labs, Penzias and Wilson, working on sensitive microwave antennas for satellite communication. And they kept picking up this persistent, faint background noise.
Like static.
Yeah, a very faint, uniform hiss coming from all directions. They tried everything to get rid of it. They famously cleaned pigeon droppings off the antenna, checked all the electronics, pointed it different ways, but the noise wouldn't go away. It was cosmic.
And what were the specific characteristics of this noise once they realized it wasn't pigeons?
It was a totally new kind of cosmic radio emission, and it was remarkably isotropic. That means its intensity was almost perfectly uniform no matter where they pointed the antenna in the sky. And crucially, its energy spectrum, how the intensity varied with wavelength, perfectly matched the theoretical spectrum of a black body radiator heated to just about 3 Kelvin.
3 degrees above absolute zero. That sounds incredibly cold and faint.
It is faint in terms of temperature, but its significance is enormous. The energy density of the CMB, it's around 10-12 ergs per cubic centimeter. That sounds tiny, but when you integrate it over the entire observable universe,
It adds up.
it adds up hugely. Its total energy density actually exceeds that of all other forms of electromagnetic radiation, combined all the starlight, X-rays, everything else floating around in the vast spaces between galaxies. The only thing with more energy density in the universe is the rest mass energy of matter itself, EMCAS. So even though it's cold, the CMB is energetically dominant.
Wow. And this wasn't just some random noise. This radiation had actually been predicted decades earlier, right? By George Gamow.
It had. Gamow's theory and the fireball from way back in 1948. He, along with his collaborators, Elfer and Herman, had worked out the consequences of a very hot, very dense, expanding early universe, the Big Bang model. They predicted that the leftover heat from that initial fireball phase would, due to the universe's expansion, eventually cool down and stretch out into a faint, uniform microwave glow permeating all of space.
And the CMB discovered by Penzias and Wilson was exactly that predicted glow.
It was a perfect match. It was stunning confirmation.
Let's dig into Gamow's theory a bit. There was a key moment he predicted, the decoupling. What was happening around 500,000 years after the Big Bang?
Okay, so at that time, the universe was still expanding and cooling. It was about 1,000 times smaller than it is today in terms of linear scale. And crucially, the overall temperature had dropped to around 4,000 Kelvin.
Why was 4,000 Kelvin so important?
Because that's the threshold temperature below which neutral atoms can form and remain stable. Before this, the universe was so hot that it was an ionized plasma. Electrons and atomic nuclei, mostly protons and helium nuclei, were separate, zooming around freely. Light particles, photons, were constantly scattering off these free electrons.
Making the universe opaque, like being inside a star or a really dense fog.
Exactly, you couldn't see through it. But once the temperature dropped below 4,000 K, the electrons could combine with the nuclei to form stable, neutral hydrogen and helium atoms.
And neutral atoms don't scatter light nearly as much as free electrons do.
Right. Suddenly, the photons were free. They stopped interacting significantly with the now neutral matter. They decoupled. From that moment on, this radiation just streamed freely through the expanding space.
And as space expanded, the radiation cooled.
It cooled passively, its wavelength stretching in direct proportion to the expansion of the universe. The matter, the gas itself, cooled down much faster because it wasn't being constantly heated by the radiation anymore.
So the universe has expanded about 1,000 times since decoupling. That initial 4,000 K radiation stretched out, cooled down to become the 3K radiation we see today.
Precisely. The CMB is the literal relic, the fossil light from that primordial 4,000 K fireball. It's an actual photograph of the infant universe.
And the CMB's impact on hypotheses. Well, it's devastating for the alternatives, wasn't it?
Absolutely total. The discovery of the CMB, alongside Hubble's redshift, stands as the greatest achievement in observational cosmology. It definitively ruled out the original steady-state hypothesis because steady-state has no explanation for this universal background heat. It also ruled out the simple pulsating model that avoided nuclear densities, because we are literally seeing the afterglow of a single, incredibly hot, dense beginning.
This gives us an incredible look-back capability, doesn't it? We're not just inferring the past, we're directly observing it.
We are. We're seeing the universe when it was only about 500,000 years old, tens of thousands of times younger than it is today, and 1,000 times smaller.
And what does that snapshot show us?
It shows exactly what the Big Bang Theory predicted. A smooth, simple, hot cloud of hydrogen and helium plasma. There were no stars yet, no galaxies, no complex structures, just the raw material cooling down after the initial cataclysm. It's powerful confirmation.
Okay, so the CMB gives us this amazing snapshot at 500,000 years. But you know, cosmologists, they always want to push further back. How do we get evidence from even earlier, like the first minutes after the Big Bang?
Right. The CMB photons can't tell us directly about that period because the universe was opaque before decoupling. So we have to use different clues, indirect evidence, and the key lies in the abundance of the lightest chemical elements we see today.
You mean hydrogen, helium?
Exactly. Specifically helium, and particularly its heavier isotope, deuterium. When we look at the amount of helium and deuterium out there in the cosmos, especially in very old, pristine gas clouds where stars haven't processed things much, well, there's simply too much of it to be explained just by nuclear fusion happening inside stars over the last 13-odd billion years. Stars make helium, yes, but they don't make nearly enough to account for the roughly 25% helium abundance we see everywhere. And stars actually destroy deuterium. They don't make it.
Okay, so stars can't be the primary source.
No. The unavoidable conclusion is that most of the universe's helium, and essentially all of its deuterium, must have been forged in a much earlier pre-stellar stage.
The Big Bang itself.
Precisely. This Big Bang nucleosynthesis happened when the universe was just a few minutes old. Temperatures were in the billions of Kelvin, densities were approaching nuclear levels conditions perfect for fusing protons and neutrons into deuterium and helium.
So the amount of deuterium we see today acts like a fossil remnant from those first few minutes.
It's an incredibly sensitive probe of those conditions. This nucleosynthesis data is a profound indirect tool. It lets us effectively look back hundreds of thousands of times earlier than the CMB decoupling era. We're using the well-understood laws of nuclear physics to reconstruct the universe's absolute infancy.
Amazing. Okay, so fast forward past nucleosynthesis, past decoupling. The universe is now a cooling, electrically neutral gas of hydrogen and helium.
Yeah.
But it was, as the CMB shows, incredibly uniform back then.
Yeah.
So how do we get, well, structure? How do we go from uniformity to structure?
That is the fundamental question of structure formation, and the answer lies in gravity acting on tiny imperfections. After decoupling, that neutral HE gas cooled down very rapidly. Now, if that gas had been perfectly smooth, perfectly uniform everywhere,
Then gravity would pull equally in all directions and nothing would happen.
exactly, it would just keep expanding and thinning out forever, staying perfectly smooth. The crucial point is that the early universe was never perfectly uniform. The CMB shows it was almost uniform, but there were tiny fluctuations, minuscule variations in density from place to place, maybe 1 part in 100,000.
Like tiny ripples on a smooth pond. And these were the seeds of inhomogeneity.
They were the absolutely critical seeds, yes. Where did they come from? That's still a huge area of research, likely quantum fluctuations from the inflationary epoch right after the Big Bang itself. But the key takeaway is, without these initial tiny seeds of non-uniformity, the regions that were just slightly denser wouldn't have had any extra gravitational pull.
And the universe would have stayed boring.
Our sources put it nicely. Its history would have been boringly simple. A featureless, expanding gas forever. No galaxies, no stars, no planets, and critically, no possibility for the complexity needed for life. Those tiny initial ripples were essential for everything that followed.
So gravity grabs hold of those slightly denser regions.
And they start to grow. The slightly denser regions pull in more material, becoming even denser, pulling in more material still, a runaway process.
Yep.
This fragmentation of the smooth gas likely started happening seriously when the universe was maybe 10 to 100 times smaller than it is today.
Corresponding to that redshift range, Z10-100.
That's the period, yes. Giant gas clumps probably formed. First, these would eventually become clusters of galaxies. Then smaller fragments within those clumps, defined by their mass and how much they were spinning their angular momentum, collapsed further to become individual galaxies.
Okay, so once the formation of galaxies and stars got going, the whole picture of cosmic expansion kind of shifted focus, didn't it?
It did. From that point on, the overall expansion of the universe wasn't so much the gas itself thinning out, but rather the space between these newly formed galaxies stretching.
Gravity holds the galaxies together internally, but can't stop the space between them from expanding.
Exactly. Gravity is dominant on the scale of a galaxy, preventing it from expanding apart, but on the vast scales between galaxies, the cosmic expansion wins. Also, those early galaxies were likely much more active, much more violent places than galaxies like ours today.
Why is that?
Probably because they had huge amounts of gas falling into them rapidly, fueling incredibly intense star formation and feeding the supermassive black holes at their centers. This hyperactivity is likely why we see so many more of those bright radio galaxies and quasars when we look back into the deep past. They were much more common back then.
Makes sense. Now, what about the gas that didn't fall into galaxies? Did it just stay cold and neutral out there in the void?
Not quite. That material forms the modern intergalactic medium, the thin gas that fills the space between galaxies. And it didn't stay cold and neutral for long. Once the first generation of stars lit up and those active galactic nuclei started blazing,
They blasted the surrounding space with radiation.
intense, high-energy ultraviolet and X-ray radiation poured out from these first galaxies. This led to a secondary reheating of the intergalactic medium.
So it got ionized again.
Yes, this flood of radiation stripped the electrons off the hydrogen and helium atoms out there, reionizing the gas throughout the cosmos. It also heated it up dramatically, raising its temperature to tens of millions of Kelvin.
And we can actually see this hot gas today.
We can detect its faint X-ray emission, yes. Observations show this intergalactic medium has temperatures around 108 to $100 million Kelvin. It's incredibly hot, though extremely diffuse. It's also worth remembering that before this era of galaxy and star formation, the universe was chemically very simple, just hydrogen and helium. All the heavier elements, the carbon, oxygen, iron needed for planets and life.
They had to be cooked up in stars and supernovae first.
Exactly. They were forged in stellar cores and then blasted out into space by supernova explosions or powerful outflows from galactic nuclei. And cosmic rays, these high-energy particles zipping through space, they also primarily originate from these energetic galactic processes. So the complex, dynamic, element-rich universe we live in today had to be built up step by step from that initial simple plasma.
Okay, so we've built the structure we see. This whole narrative of the past. It inevitably leads us to think about the future. What's the ultimate fate? And that seems to hinge entirely on the universe's overall geometry, which boils down to its average density, right?
Yeah.
This is the big question. Determining the universe's fate. Open versus closed.
That's the crux of it, yes. It's all about the cosmic balance between the outward momentum of expansion and the inward pull of gravity, exerted by all the matter and energy within the universe. If the average density is less than a specific critical value,
When expansion wins.
expansion wins forever. Gravity isn't strong enough to halt it. That's the open model, like throwing a stone upwards so fast it escapes Earth gravity entirely. If the density is greater than that critical value.
Gravity eventually wins, pulls everything back.
Exactly. Expansion slows down, stops, and reverses into a cosmic contraction, leading eventually to a big crunch. That's the closed model.
So what do the measurements tell us?
Yeah.
What density do we actually see from the stuff we could detect, like galaxies?
Well, if you take all the luminous matter in galaxies, stars, gas, dust, and you sort of smear it out over the volume of the universe, the density you get is quite low. Current estimates put it at less than 1030 grams per cubic centimeter.
Okay, and how does that compare to the critical density needed to close the universe?
It's way too low. For the universe to be closed, the total mean density, including not just galaxies, but also intergalactic gas, and importantly, dark matter and dark energy, would need to be about 30 times greater than that density we see just from the galaxies.
30 times. That sounds like a big gap to fill, even with dark matter.
It is a very significant gap. Based on surveys of all known forms of matter and energy, reaching that critical density just seems highly unlikely right now. The universe appears to be below, or perhaps very close to, but not significantly above, that critical threshold.
But there's an even more decisive argument, isn't there? One that takes us way back to the beginning again, the deuterium argument.
Ah, yes. This is arguably the most powerful piece of evidence we have supporting the open, or perhaps flat, which also expands forever, model. It comes back to Big Bang nucleosynthesis.
The cooking of elements in the first few minutes.
Right. Deuterium, that heavy isotope of hydrogen with 1 proton and 1 neutron, is particularly interesting because its formation rate is incredibly sensitive to the density of ordinary matter, protons and neutrons, present during those first few minutes.
Yeah, so.
If the density was higher, protons and neutrons would have collided more often, and more deuterium would have fused further into helium. If the density was lower, fewer collisions would occur, leaving more deuterium unfused.
So the amount of deuterium left over today is like a cosmic density gauge, calibrated in the first 3 minutes.
That's exactly what it is. We can measure the abundance of deuterium in distant, ancient gas clouds that haven't been contaminated much by stars. We find it's about 50,000 times less abundant than ordinary hydrogen. Now, we use the established laws of nuclear physics to calculate what density of ordinary matter must have existed back then to produce exactly that observed amount of deuterium.
And what's the answer? Does it match the critical density?
Not even close. The density calculated from the deuterium abundance is roughly 100 times less than the critical density needed to close the universe.
Wow, a factor of 100. That's not just missing the target, that's nowhere near it.
It's a huge discrepancy. It strongly suggests that the density of normal baryonic matter is far too low to ever halt the cosmic expansion. This deuterium measurement provides the major physical argument backing the open model, or a flat, dark energy-dominated model that also extends forever. It's why most cosmologists favor this picture, even with the added complexities of dark matter and dark energy. The universe seems destined for perpetual expansion.
And this fact of perpetual expansion, it leads us, kind of unexpectedly, to solving that really old puzzle. Why is the night sky dark? The cosmological solution to Olber's paradox.
Right, the famous photometric paradox. It seems simple, but it's profound. If you assume the universe is infinite in extent, infinitely old, and uniformly filled with stars.
Then no matter where you look, your line of sight should eventually hit the surface of a star, right?
Exactly. The entire night sky should be blazing bright, as hot as the surface of an average star, maybe 5,000 to 10,000 Kelvin. So why is it dark?
People used to suggest maybe dust blocks the light.
Yeah, but that doesn't work. If dust absorbed all that starlight, the dust itself would heat up until it glowed just as brightly as the stars it was blocking. The static infinite model just fails to explain the darkness.
So how does modern cosmology, with its expansion, solve it?
The modern cosmological view, confirmed by the observed expansion, redshift, and the finite age implied by the Big Bang and CMB, provides the complete answer. The most crucial factor is the redshift caused by expansion.
How does the redshift make the sky dark? I get that it shifts light towards red, but it's still light energy coming towards us, isn't it?
It is, but two things happen. First, as photons from very distant galaxies travel across billions of light years of expanding space, their wavelengths get stretched enormously. This stretching means their energy decreases significantly. Energy is inversely proportional to wavelength. The light gets degraded, thinned out.
Okay, so distant light arrives much weaker than when it started.
Much weaker. Second, there's the finite age. We can only see light from objects whose light has had time to reach us since the Big Bang, about 13.8 billion years ago. There isn't an infinite amount of time for light from infinitely faraway stars to arrive. The combination of this finite horizon and the energy-sapping redshift effectively cuts off the contribution from the most distant regions. It shifts that potential energy into the very long wavelength, low-energy radio part of the spectrum, far too cold to make the sky glow visibly hot.
So the darkness isn't because the universe is empty or finite in stars, necessarily, but because it's expanding and has a finite age. And this darkness, it's actually essential for us.
Absolutely essential. This leads directly to expansion and the conditions for life. Think about it. If the universe were static and infinitely old, as Olber's paradox assumed, the background temperature really would be thousands of degrees Kelvin.
Nothing complex could form. No molecules, let alone life.
Exactly. Forget organic chemistry. Even simple molecular compounds couldn't stably exist at those temperatures. The cosmic expansion, by allowing the universe to cool down dramatically, by creating the cold, dark background we observe, is what provides the necessary low-temperature environment for complex structures like molecules, planets, and eventually life to emerge and persist. Our dark, cool night sky isn't just a curiosity. It's a fundamental prerequisite for our existence.
Okay, we've charted the past, understood the present state and its expansion. Now let's steel ourselves and look into that vast, mind-bending future. Assuming the open model holds true, we're talking about truly eternal timescales. But just quickly, before we dive into that deep end, what would have happened in the closed model scenario, just for contrast?
Right, the closed model, though the evidence is against it. If it were true, the expansion would eventually stop, perhaps 50 billion years from now, give or take. Then gravity would take over completely, and the universe would begin to contract.
Everything rushing back together.
Yes, accelerating inwards, eventually collapsing into an infinitely dense singularity, a big crunch. Basically, the Big Bang played in reverse. The whole cycle, expansion then contraction, might take around 100 billion years total.
Would it bounce? Could it repeat?
That's a big theoretical question. Could it bounce and start a new expansion? Maybe. But critically, there's no reason to think subsequent cycles would be identical to ours. The fundamental constants, or even the types of elementary particles produced, could potentially be different each time. No guarantee of a perfect cosmic reset.
Okay, interesting, but let's stick with the evidence.
Yeah.
The open model scenario seems to be our likely future, and here, the timescales just become astronomical, doesn't even cover it.
Right.
We're talking about changes happening over periods that make the current 14 billion year age of the universe seem like an eye blink.
Completely dwarfed, yes. We have to think in powers of 10, many powers of 10. The first major milestone is really the end of the era of stars as we know them. At about 1014 years, that's 100 trillion years from now.
100 trillion. Okay.
All the longest-lived stars, the small red dwarfs, will finally exhaust their hydrogen fuel. They won't explode, they'll just slowly fizzle out, becoming cold, incredibly dense spheres of degenerate matter called black dwarfs, probably about the size of the Earth, but with the mass of a star, just cold and dark.
So the universe goes dark, essentially.
The stellar lights go out, yes. And then structures start to actively dissolve. Around 1015, a quadrillion years.
Okay, now you're just making numbers up. A quadrillion.
Slight chuckle. Feels like it, but these are the calculated timescales. Over that period, random gravitational encounters, stars passing near each other within galaxies, will have had enough time to gradually nudge planets out of their orbits. Virtually all planets will eventually be ejected from their parent black dwarf stars, doomed to wander alone in the darkness.
So lonely planets drifting in an eternally dark void. Grim. Does anything happen to the galaxies themselves?
They dissolve too, eventually. Over an even longer timescale, maybe 1019 years, that's 10 quintillion years, these same slow gravitational interactions will eject the vast majority, maybe 90% or more, of the black dwarfs out of their host galaxies.
The galaxies evaporate.
Effectively, yes. Most stars get flung out into the intergalactic void. Meanwhile, the remaining stars and the central supermassive black hole in the galactic core will tend to spiral inwards due to gravitational interactions, eventually merging into one truly colossal black hole at the center of what used to be the galaxy.
This sounds like the era of isolation.
That's a good way to put it. Galaxies as distinct, structured collections of stars cease to exist. The average distance between neighboring stellar remnants, these cold black dwarfs, will have expanded enormously due to cosmic expansion, from light years today to many megaparsecs, and continuing to grow indefinitely. The distance to the nearest star could be greater than the distance to the furthest quasars we see today. The sky will be utterly, profoundly black.
Right, this is getting seriously weird. Now we're entering timescales that are just words fail. And this next bit depends on whether protons are truly stable, right? Which is a big if.
It's a huge caveat, yes. Many grand unified theories in physics predict that protons should eventually decay, perhaps on a timescale of 10 years or longer. If they do, everything dissolves into radiation much sooner. But let's assume, for the sake of exploring the ultimate limits, that protons are stable forever.
Okay, assuming stable protons, what happens next?
The timescales become truly mind-numbing. At around 10 phi years, something very strange is predicted to happen due to quantum tunneling effects, even at near absolute zero temperature. all solid matter, including those incredibly dense black dwarfs, is expected to essentially liquefy. They would arrange themselves into minimum energy states, becoming perfect spheres of cold, degenerate liquid.
Solid stars turning into liquid drops,
Yeah.
even at zero temperature.
Quantum mechanics over immense timescales allows for seemingly impossible rearrangements, but even that's not the end. Over perhaps 10–1500.
10 to the 1500.
Acknowledging the absurdity. Yes, it's a number so large it's practically meaningless. But theoretically, over that time, continued quantum tunneling and potentially incredibly slow nuclear processes would convert all remaining baryonic matter into the most stable element, iron. You'd have these vast, cold, isolated liquid drops of pure iron floating in the void.
Just iron spheres drifting apart forever. Is that the end?
Almost. The last bastions of structure are the black holes, both the stellar mass ones formed from stars and those supermassive ones lurking in galactic centers. For a long time, they were thought to be truly eternal endpoints.
But then Hawking radiation came along.
Exactly. Stephen Hawking showed that due to quantum effects near the event horizon, black holes should slowly radiate energy away, effectively evaporating over incredible timescales. The rate of evaporation is slower for more massive black holes.
So even black holes die eventually. How long does it take?
For a typical stellar mass black hole, maybe 10 times the mass of our sun, the evaporation time is calculated to be around 10 years. Still an immense time, but short compared to the iron sphere era.
And the supermassive ones, the galaxy killers.
They take much longer. A supermassive black hole with 1 billion solar masses, like those in the cores of large galaxies, would take something like 10 years to evaporate completely.
10 to the 91.
It's the final countdown, really. Even those iron spheres might eventually, through quantum tunneling again, collapse into neutron stars or black holes themselves, which would then evaporate relatively quickly on these timescales.
So no matter how you slice it, even if protons decay sooner, the ultimate end is nothingness.
Pretty much. In all plausible scenarios, the ultimate fate of the universe in the very far future is to become an incredibly dilute, cold, dark, expanding void containing nothing but extremely low energy, ultra-long wavelength photons and neutrinos dissipating forever. All structure, all complexity, all possibility of life is fundamentally a temporary phenomenon on the grandest cosmic timeline.
Wow, okay. That vast, cold, empty future. It kind of brings us crashing back to the present and maybe the most profound question of all. Given that bleak ending, why did our universe follow this particular path, one that did allow for complexity for stars, planets, and ultimately us to exist even for a cosmic moment? This gets to the heart of the anthropic question, doesn't it?
It really does. We look around and we see a physical world governed by what seem to be fundamental laws and constants. There are the 4 basic forces, right? Electromagnetic, gravitational, the weak nuclear force, and the strong nuclear force. Each of these has a characteristic strength, often represented by a dimensionless constant.
Like the fine structure constant for electromagnetism.
Exactly, alpha. And there's one for gravity, alpha, one for the weak force, one for the strong force. And the values of these constants, well, as far as we know from fundamental theory, that could potentially have been different. Yet they have the specific values they do. And these values seem interconnected in surprising ways.
You mean like that bizarre connection Paul Dirac noticed back in the 30s, the Dirac relationship? What was that again?
Yeah, that was a stunning observation. Dirac was puzzled by the enormous difference in scale between the universe and fundamental particles. He pointed out this incredible numerical coincidence. If you take the ratio of the size of the observable universe to the size of a proton, that number is roughly the same as the ratio of the strength of the electromagnetic force between a proton and an electron to the strength of the gravitational force between them.
Wait, the size of the whole universe compared to a proton is related to the strength of forces between particles. How can that be?
It's truly mind-boggling. It suggests some deep link between the vastness of the cosmos and the fundamental rules operating at the quantum level. The sheer scale of the universe seems somehow encoded in the relative strength of gravity and electromagnetism.
That is deeply weird.
It is. Now, Dirac himself went on to hypothesize that maybe the gravitational constant, g, changes over time to maintain this relationship as the universe expands, an idea that current observations don't support. G seems pretty constant. But the numerical relationship itself remains this astonishing coincidence that hints at deeper connections.
And these kinds of coincidences, these seemingly just right numbers, paved the way for what's called the anthropic hypothesis, right? Formalized by Robert Dicke, not Dix, I think, around 1961.
Yes, Dick, you're right. The core idea of the anthropic principle, in its weaker form at least, is essentially a selection effect. It proposes that the fundamental constants and conditions we observe in the universe must be the way they are, because if they were significantly different, life capable of observing the universe like us could never have arisen in the first place.
Let's say.
So we find the universe has these properties because if it didn't, we wouldn't be here to notice. That's the basic logic. It doesn't necessarily explain why the constants are what they are, but it highlights the constraints. Let's look at some specific examples of this fine-tuning. The first one is pretty straightforward. Age fine-tuning.
How is the age fine-tuned?
Well, think about the elements needed for life as we know it: carbon, oxygen, nitrogen, iron, etc. Where did they come from?
They're made in stars, and especially the heavier ones, in supernova explosions.
Exactly. And supernovae come from massive stars that live relatively short lives, maybe tens or hundreds of millions of years, up to perhaps a billion years for the ones that make key elements. So the observed age of our universe, $2, which is around 14 billion years, cannot be vastly older than the timescale for supernovae, $2 approx 199 years.
Why not?
Because if the universe were, say, trillions of years old, all the stars capable of producing and dispersing those heavy elements would have died out long ago. We'd be living in that era of black dwarfs we just talked about. The raw materials for rocky planets and complex chemistry wouldn't be readily available in interstellar space anymore.
So we necessarily exist in this specific cosmic epoch, this window of opportunity, when heavy elements forged by past stars are abundant and stars like our sun are still shining.
Precisely. Observers like us require a universe old enough to have had supernovae, but not so old that all stellar activity has ceased. But the tuning gets much, much sharper when you look at the fundamental forces, especially the weak interaction constant, the weak force that governs things like radioactive beta decay and neutrino interactions. Why is that so critical for life? It seems less obvious than gravity or electromagnetism.
It's absolutely crucial for two main reasons: Big Bang nucleosynthesis and how stars, particularly supernovae, work. Our sources point out some incredibly narrow constraints on alpha.
Yeah, like what?
First, if alpha were just slightly smaller than it is, the balance between proton-neutron conversion in the first few minutes would have shifted dramatically. The result: almost all the primordial matter would have fused into helium. You'd have a universe that's nearly 100% helium. A helium universe. No hydrogen means no long-lived stars like the sun, no water, H2O. Basically, no life as we know it.
Exactly. No water, no organic chemistry, lifeless. Now, what if alpha dollar were slightly larger?
What happens then?
Then the opposite problem occurs. Neutron decay would have been more efficient, or fusion processes different. You'd end up with virtually no helium produced in the Big Bang. It would be almost pure hydrogen. This would completely change how stars evolve, their lifespans, everything, and perhaps even more critically,
Yes.
the weak interaction governs how neutrinos interact with matter. This is absolutely vital for supernova explosions. It's the pressure from neutrinos streaming out of the collapsing core that actually blasts the outer layers of the star into space, dispersing those heavy elements. If alpha dollar were even slightly different, that neutrino interaction changes completely. Supernova might not explode successfully.
So a tiny tweak to the weak force and the elements needed for life stay locked up inside dead stars.
Correct. No carbon, no oxygen distributed through the galaxy. It's an incredibly sensitive parameter, set just right. It's like a cosmic thermostat dialed to an astonishingly precise degree.
Okay, fine-tuned forces.
Yeah.
What else needs to be just right? It feels like even the amount of stuff matters.
It does. Another crucial parameter is the proton-photon ratio, S, sometimes called the baryon-to-photon ratio or related to the universe's entropy. Basically, it tells us how many photons, particles of light radiation, there are for every proton or neutron baryonic matter. The observed value is about $0 approx 188, meaning nearly a billion photons for every proton.
Why is that number important? And can physics explain it?
Physics currently has no fundamental explanation for why this ratio is 188, and not, say, 105 or 10, $12, but the anthropic principle puts limits on it. It seems S cannot be much larger than about 199.
Why? What would happen if there were way more photons relative to matter?
If S were significantly higher, the radiation pressure in the early universe, the outward push from all those photons, would have been overwhelmingly dominant compared to gravity. It would have completely prevented matter from clumping together via gravitational instability.
So too much initial heat and light, And gravity never gets a chance to form galaxies or stars. The universe just stays a smooth, hot gas forever.
Exactly that. Structure formation becomes impossible. So we need this specific balance, not too many photons per baryon. And finally, even the masses of fundamental particles seem fine-tuned.
Like the proton and neutron mass difference.
Yes, that's a key one. The neutron is slightly heavier than the proton. If it were the other way around, or if the difference were much larger or smaller, the whole chain of Big Bang nucleosynthesis would be drastically different. Maybe no deuterium forms, or maybe all protons decay. Also, the specific mass ratios between particles like protons, neutrons, and pions are critical for the nuclear reactions inside stars that create elements like carbon, particularly the triple alpha process that makes carbon from helium. It relies on delicate energy resonances that only work because the particle masses are what they are.
It's like a whole series of cosmic coincidences lining up perfectly.
It certainly appears that way.
Yeah.
Which brings us to the ultimate conclusion on life's place.
What's the takeaway from all this fine-tuning?
The inescapable conclusion, based on our current understanding, is that our observed real universe appears amazingly suited, as the source material puts it, for the emergence and development of life. If that initial set of fundamental constants, particle mass ratios, the proton-photon ratio, if any of those have been significantly different, theoretically, it seems they could have been different, the resulting universe would likely have been structurally simple, chemically barren, and utterly lifeless.
So our existence isn't just some random accident on one planet. It's tied into the fundamental structure of the entire cosmos from the very beginning.
That seems to be the implication. The evolution of life here on Earth can't really be understood in isolation. It appears to be a natural, albeit perhaps rare, consequence arising within the grand evolutionary process of the entire universe, stretching all the way back to the Big Bang itself. #outro.
Wow. Okay, that was quite a journey. We've gone from this incredibly dense, almost unimaginable initial particle, through the forging of the first elements in just minutes, watched stars and galaxies form over billions of years, and then peered into a future stretching for, well, practically forever, ending in cold darkness and evaporating black holes.
It's the entire history and future laid out by physics and observation.
And we saw how crucial those observational breakthroughs were, Hubble's redshift showing expansion, and especially that discovery of the cosmic microwave background, the 3 Kelvin afterglow. That really was the nail in the coffin for the old static, unchanging universe models, wasn't it?
Absolutely. Those observations provided the definitive, ironclad proof. They forced us to accept that the universe has a history, that it evolves dramatically over time.
So the core message, really, is that cosmology reveals a universe that is fundamentally evolutionary. It changes. And maybe even more profoundly, our own existence seems intricately linked to this incredibly precise, maybe even unlikely tuning of the fundamental laws and initial conditions operating over these vast cosmic timescales.
That's it, exactly. We seem to live in a universe that is structured in just such a way that complex beings like us can emerge and eventually develop the capacity to actually ask these questions about the universe itself. It's quite remarkable.
Well, it really is. So here's the final thought, the thing for you to maybe mull over after this deep dive. We can directly see the universe when it was 500,000 years old, using the CMB photons, that fossil light. But that crucial era of the first few minutes, when the light elements were forged, that remains hidden from us optically because the universe was opaque.
Right, we infer it from nucleosynthesis calculations and the element abundances, but we can't directly image it with light.
So what's the ultimate frontier? How could we possibly see even earlier?
Well, there's one particle that interacts so weakly it could potentially stream right through that dense early plasma, the neutrino. The ultimate goal, the holy grail for observational cosmology right now, is probably neutrino astronomy, specifically detecting the relic neutrinos from the Big Bang.
Neutrinos left over from the Big Bang.
Exactly. They decoupled from matter even earlier than photons, when the universe was maybe less than 1,000th of a second old and temperatures were far higher. If we could detect these incredibly elusive, low-energy relic neutrinos today,
What could they tell us?
they could potentially give us direct information about the universe when it was practically instantaneous, maybe even confirming or constraining ideas about that initial supernuclear particle state directly. It's an incredibly high goal, technically maybe the hardest challenge in experimental physics. But the potential payoff, a direct window onto the first fraction of a second, fully justifies all the immense effort going into developing this extraordinarily difficult field. That's the next great observational frontier.